with that. So like basically once a month we'll have a new topic, and every second week we'll meet. And hopefully the few weeks gives you a bit of time to go away, work on some of the things if you want. Obviously, it's completely optional. Yeah, it's up to you how much you want to get out of it, really. And if it's too easy, well, then you can try and apply some of these to problems that you any other problem that you want, really. Okay. So let's just jump in. Okay, this is the GitHub page that I just pushed it. But so if you haven't already, I'd suggest opening it in Colab. It's the simplest way just to get it running in a way that we all have the same environment. But if you've already got it open locally, that's fine as well, obviously. Okay. Yes, so just as a really general introduction, but I expect most of you have come into contact with Monte Carlo before. But Monte Carlo just refers to any method that uses random numbers to produce its numerical results. Or in the case of most things that we do, they're actually pseudo-random, and we'll get back to what that means. So these techniques were actually pioneered by physicists. The technique itself was named by Stanislav Ulam. He was a Polish physicist who was actually working on the Manhattan Project. So he literally created these methods for some simulations he was doing for making nuclear bombs. And Fermi apparently had played around with them in the 30s, but he never actually published his results. So like, yeah, he's often credited as well. And yeah, so Ulam had named this after the Monte Carlo casino, its famous casino in Monaco, obviously because of its connection with chance and gambling. So there's three main classes of problems that we apply Monte Carlo to. Just getting random samples from distributions, optimization problems, and then very commonly integration. So you've probably already encountered these things. And yeah, these are used extensively across all of particle physics, all of these methods. So optimization might be like trying to find the maxima of functions. Integration, obviously, we do a lot, which has a lot of applications in statistics as well. And random sampling we do all the time just to do simulations of, say, Poisson statistics and so on. Okay. So I thought I'd start really at the basics with a uniform random number generator, but where we actually look at like the nuts and bolts of it. Because a lot of people, I don't know if people just skip over this part. Typically these days you just use whatever is implemented already, which is actually these days is a good thing. It used to be just like the standard random number generators weren't very good. And they weren't, you definitely didn't want to use them in simulations. And that comes down to basically they didn't have good statistical properties, and they may have small periods. So the type of random number generators that we're going to work with are pseudo-random number generators. And it's good, you have to know that these are completely deterministic. And they're normally implemented as a chain. So we've got a whole list of numbers, and there's a state in the chain, and at each point you can move to the next point in the chain, and you'll just get a sequence of numbers that jump around in some pseudo-random way. So you can, it's also worth knowing that you can actually get completely random things. You can buy hardware that will spit out completely, truly random numbers. It'll take it from things like something like some sensor that it's got on board, or some decay of something inside this little thing. You can also just get them online. If you go to random.org, it'll spit out random numbers to you, and you can write a little API, or you can use their API. You can write a thing to grab these random numbers. You probably don't want to do that for a simulation that needs speed. But truly random numbers are available if you want them. Yeah, so just as a really simple example, there's a thing called the linear congruential generator. And it's just this series here. So you choose some initial starting point, and then you have these constants A, C, and M. And so it's just this simple equation, and then you take it mod m, and then that gives you the next point. Now, that's incredibly simple, but if you just choose whatever numbers for these, and I invite you to do that if you wanted to play around, you won't necessarily get a very good random number generator. So if you choose A, C, and M very carefully, though, and Wikipedia has a list of parameter choices, and for a long time, it's like these were just the standard random number generator you could use. In particular, like if you choose M to be very large, so we have an example here where it's going to be 2 to the 31. You can have things with a very, very long period. And that's, at least that's one thing you kind of want. You don't want to return back to the same numbers very quickly. That wouldn't be very random. And so this approximates the uniform distribution, i.e. it'll tend towards a distribution that just looks like this. And it's a very fast thing to compute, and it doesn't take up much memory because the state is just this number here, which will be that, like whatever length you decide. But it's not particularly good in higher dimensions. But we're just going to use it here just to play around with. Okay. So yeah, like I was saying, it's pseudo-random because we have this deterministic chain, and we needed to start it somewhere with a seed. Now, seeds are really useful though, because when we're if you're just doing some code, writing some code, developing some code for a simulation, generally you might want to just take out the random part of it so that you can bug check and do things. So it's if you having a seed can be useful in that way, because you can at least start with a known seed and then make sure you're getting consistent results. And then at some later point, probably just want to take it from some random place like the system clock or something, just so you start at a random part of the chain and you'll always get random numbers. Okay, so this one that I've coded up with just some of the parameters, standard parameters, gives you pseudo-random integer that has a length of 2 to the 31. So this fits in a standard like 32-bit integer. And we want to produce a number which is between 0 and 1. So at the end, we output dividing it by 2 to the 31. So this will produce a random number between 0 and 1. And that's sort of the standard thing to do, so that then you can take that number and then we'll be able to transform it to whatever distribution we want. Okay, yeah, so you can really see this is just the A times xn plus c. This is mod in Python, and that's the m value. And then we keep the seed value as a global variable, and then you just increment it after each step. So what does that look like? I've already run it. So every time you now run it, you'll just get some new random number will get spat out between 0 and 1, with about 32 digits of in your float. So let's create a larger sample and create a histogram of it. So we'll create a NumPy array. Here I'm just going to do 10,000 points. And then we'll bin them. We'll create a histogram with 40 points. And you can see that's looking pretty uniform. Now, there's a whole bunch of, there's like suites of statistical tests that you can apply to random numbers. The simplest you might imagine doing is check that the mean tends towards the expected value. So this is just doing this integral. So for the uniform distribution between 0 and 1, that should be a half. So the mean of our sample was 0.500, which is about what you would expect given we did 10,000 points. You'd expect about 3 or 4 digits of accuracy. So that's pretty good. Yeah, this type of random generator doesn't pass all the statistical tests, but it is generally good enough for some simple applications. Yeah, so then typically, and what we're going to use in the rest of this notebook is we'll just use the standard one that's built into NumPy. So NumPy has a whole bunch of random number generators, but we're going to start with the uniform one. You can just specify here the minimum X value, maximum value, and size is how many numbers you want, and then you'll get an array. And it uses a thing called the Mersenne twister, which is based on Mersenne primes. And yeah, it's a very high quality generator. It's not like the most lean in terms of memory use and computation, but it's a good balance. It's still apparently not cryptographically secure, and I don't know a lot about that, but there's like another level of like cryptographically secure random number generating algorithms. Okay, so let's do something useful. I think the first thing I learned, and I enjoyed this as an example, is just calculating pi from random numbers. So just noting that the ratio of the area of the unit circle to a square which is bounding it is pi over 4. Then if we throw some random points into the xy plane, we should find that we would have the same number of points, the same ratio of the points inside the circle to what was thrown at the whole square. Okay, so what does that look like? So let's just do this example really quickly. So we'll throw 10,000 random points between -1 and 1. So that covers the whole unit circle. And then we'll plot them on this in this graph here. And now here I've put in the unit circle. So we've got this unit circle with all these points that are randomly, uniformly distributed across X and Y. And now if we count up how many points are within this circle versus how many are in the whole box there, we get 7,858 for this example. I'll just do another one. We're doing it live. So it looks slightly different this time. 7,842 inside the circle. So then we can estimate pi from this just by taking the number of points in the circle divided by the number in the square multiplied by 4 using that formula. And here we got 3.13. So it's not a great estimate, but it will converge as you increase the number of points that you sample. So as an exercise you can play later, write a function which will calculate the number of pi using this method for a given number of points that you throw into the square. And then you can make a plot which will illustrate how this converges to the number of points, converges to the true value of pi for increasing number of points. And this is sort of the key thing that, the key property of Monte Carlo methods that you want to look at is how quickly your method will converge to the true number as you increase the number of points. And you want to have something that has good convergence, otherwise, like that just means good speed. You can do fewer samples and get to the right result. So this is it's a good way to think about what you're doing, like how it scales with the number of samples you do. Okay. So let's look at sampling from distributions, which is one of the most common applications you probably encounter needing random numbers for. So above, we were just sampling between 0 and 1. And we can use this and transform it into any distribution that we want. And that's what NumPy would be doing behind the scenes most of the time. So the simplest method is called guess and check. So it's similar to what we just did with that calculation of pi. But here you throw random points at a region and we're going to keep those below a curve rather than those that were inside a circle. So it's easiest just to see this in an example. So here we've got the standard normal distribution. So it's got standard deviation of 1 and its mean is at 0. And I've thrown random numbers at this box from -5 to 5 and between 0 and 0.5. Now, if you throw out all the points that are above that curve, so you just keep these ones here, and yeah, we can do this live. So here, this is generating our random numbers, plotting them as a scatter plot, including a curve of the standard normal. And then here, this just loops over. We create a new array that's empty, And we just loop over it and keep points that are below the normal distribution. Oops, I need to run that. So yeah, here are our samples which fell below the normal distribution. And when we histogram that, you see that it follows the distribution. And I've only done 1,000 or whatever it was, 10,000 points, because if you do too many, you just can't even see the points in the plot. So as you do more and more samples, you'll see that these samples will tend to exactly the distribution. So yeah, that's behaving as we like. But to do that, our box here is about 5 times larger than the curve under the curve of the normal distribution. So we're throwing out 4 points for every single point we generate. So it's not very efficient. So a better way to do it. Well, okay, so I've written an exercise if you wanted just to do this method for some whatever arbitrary distribution you pass to it. And an obvious gain of efficiency you could get is if you only throw y values that are at the maximum. You need to throw y values that are at least above the maximum, otherwise you'll clip your function. But you could definitely get some extra efficiency. Like all of these points up here are wasted. So if your maximum y value is set to be the maximum of your function in the range, then you'll get a bit more efficiency. So you can play around with doing that. But the standard method that is used is what's called inverse transform sampling. So yeah, what if we could just simply throw random numbers into the exact shape that we want? So what's that going to look like? So here's our uniform sample, and we want them to end up in this random normal distribution. And you think like it should be a way that you can just apply some sort of smearing to this sample and that would produce that. And yeah, of course you can do that. So for a distribution that you want to generate, P of X, you can achieve this just by applying the inverse CDF, P of X. Well, that should be P of X inverse. I didn't even do this as math. To the uniform distribution. So if we generate some uniform random numbers, and then you can just feed them into the normal CDF. So they call that the PPF in Python. This is in SciPy, this function. Then the values that come out will be normally distributed. Now, to sort of visualize this better, get a bit more intuition for what's happening, this is the CDF, the inverse CDF here. So that's the cumulative distribution function. So we're integrating the normal distribution from 0 to something, and then we're taking the inverse of that function. So because it's a probability distribution, the maximum value is 1. So you have to integrate up to infinity to get all the probability of the normal distribution, or down at minus infinity is where you get 0 probability. So this is just a curve that goes between 0 and 1. So now if I throw random numbers, so on the x-axis, here's my uniform random distribution. If I throw random numbers between 0 and 1, and then I feed them into the inverse CDF, then the y value that I get is going to follow the normal distribution. So this is sort of the visual, this visually helps me sort of picture what's going on. So like this little region here, so each bin in X here is meant to be uniformly sampled. And so when the function is steep, you sort of smear out some equal number of probability over a wider range up here. So you're stretching out the distribution. And when the gradient becomes smaller, all the points over a wide range here get bunched up. And so you get more points here. And so you can do this for any function. So if you and I do this all the time, like if I'm generating, I want to sample points from some distribution of energy, then you can calculate what that distribution of energy is, normalize it, calculate an inverse function of that, and then pass random uniform values into it, and then you get random draws of, say, energy per particle. And so there's an exercise to do that for some given function. So I suggest doing that because that is a common task that you might come across. It's a handy thing. And you can just write a function that you can use again and again for that. Okay, any questions? I should stop and ask. Do we have any questions? It's all very simple so far. Okay, I'll keep moving. If you just want to put other questions in the chat or anything, then I can look it up later, or you can always email me. Okay, so moving on. Now, I feel like this stuff gets a bit more interesting, a bit more fun. There's a typo. So now we're going to look at Markov chain Monte Carlo. So this inverse transform sampling is great when you've got one dimension, but as soon as you want to do more than one dimension, then this doesn't work. And so you would have to fall back on that guess and check method, which you can do in multiple dimensions. But it becomes extremely inefficient as the volume of your function gets smaller compared to the box you're throwing things in. So we're going to use what's called the Metropolis-Hastings algorithm. So we'll get back to what that is. It's a type of Markov chain Monte Carlo. So Markov chains are processes where you have a series of steps, and each step only depends on the current state or the previous step that you've taken. And then this is just random. So basically, the simplest Markov chain you can imagine, we'll make that, we'll just perform a random walk. So you start at some point, you're going to start at 0, 0. I'm going to take some random step in the X and the Y direction. You can draw that from whatever distribution you want. I'm going to use the normal distribution. So let's define a number of steps to take. We're going to create an array to store this chain. I'll set our starting position at 0 and 0, define our step size. Like I was saying, so the size we'll use to define the standard deviation of a normal distribution. And then so for taking this number of steps, we just start where we were and then take a random step. So this generates a random number, mean of 0, sigma of the step size, and this 2 gives it to you in 2 dimensions. So it gives you 2 random numbers, and that'll be our X and our Y step. So we do that, take 100 steps, and then we plot it. So we started here at the in the middle, and we've just taken a bunch of random steps around this space. Actually, no, sorry, 0, 0 is there. We started down here and we walked up around here and ended up here. So every time you do this, you'll take a different random walk and end up somewhere else. So, okay, how are we going to use this to actually, it doesn't seem very useful for producing something in a distribution. But it turns out as you increase the number of steps, so let's do like 100,000 steps. And this time we're going to constrain it to a box. So if it wants to step outside the box, we'll say, no, we're not going to accept that step. So we're just going to add one more bit to the code where we propose a random step. So this is the same as before. It only depends on the previous step. We create a random step. But what we're going to do is we're going to say if that step's outside the box, outside some X max or Y max, then we won't accept it and we'll try and take another random step. So it's a very simple addition, and that should keep it within a box. So we'll take 100,000 steps and see what that looks like. So now we've visited the box everywhere, you can see, between -5 and 5. And when we plot histograms of that, we're basically visiting everywhere in the box equally. Now, it's not exactly equal because you need to do this a lot to visit everywhere since the box is quite large. And the edges won't be sampled very well in the type of algorithm I've chosen. But effectively what we're doing here is we're sampling this 2D space equally. So we've now got a 2D random number generator. Okay, so that's great. But what if we want to sample some arbitrary distribution? Well, we need to introduce one more step. And this is where the Metropolis Hastings algorithm comes in. So if we want to sample from some arbitrary distribution, we'll call it f of s, then we need to somehow tie the likelihood of keeping a given step. So before we just had one condition. When we step outside the box, we say, no, we're not going to accept that step, try again. So what if we instead tie the probability of taking a step to this function f of s? Metropolis Hastings is just the simplest way you could imagine doing this, is you take the function at the proposed step, and then you divide it by where you are currently now, so the function at the position you are now. And if that is greater than some random number that's generated between 0 and 1, then you keep that step. So what this will generally do is if the function value is increasing, is higher than where you are now, then you're more likely to take that step. Well, you will definitely take that step if it's higher, because that will always be greater than 1. But there's always a probability that if the step is somewhere to a region that's the function value is smaller, then there's a probability that you will step in that direction, but it's going to be a probability less than 1. So it's not immediately obvious that that's going to do what we want, but let's just have a look. So let's sample a 2D normal distribution using this algorithm. So all this other machinery is exactly the same as before, but we define our 2D distribution as just the product of two normal distributions in x and y. And we just add this one condition to our when we're taking a step. So we generate, this is sometimes called a proposal step. And then so you test it. It's just the ratio of the function at the new point versus where you are now. And then, compare that to a uniformly random number between 0 and 1. And so when we do that, then it will take a bit longer because now sometimes the steps won't work. It's kept this chain, this Markov chain, it's kept it around 0. And the distribution, when we plot the histograms, do appear to be pretty normally distributed around 0. So that's a pretty simple thing to do, but straight away we're now sampling from a two-dimensional normal distribution. Now, you do have to keep in mind that Markov chains aren't perfect in that, so it's nearby points are going to be correlated because you are literally taking steps through the distribution. But if you take random points now from this large sample, then all of these will be, they are representative of the distribution. The other thing that you have to worry about is that we knew exactly where to start this one in the middle near the peak. But if you started somewhere way away from the peak, like out here, then obviously those initial points are going to be way outside where you would expect to find points in the distribution. It's like in these 10,000 steps, it didn't walk anywhere outside, say, -4 to 4. So if you started out here at like -5, then those initial points are not going to be statistically likely. And so you take care of this by just throwing away some number of your initial points, and that's called burn-in. So Markov chains typically need burning in when you're working in higher dimensions or with functions where you don't know where the maxima is. Now, obviously, you can use this to find maxima. That's a simple way to find maxima of functions, but it's not going to be necessarily the most efficient. And then the other thing to note is that I sort of glossed over that you have to choose the step size carefully. if you chose your step size to be too large, then you're going to jump around the distribution and not sample it. So these numbers, it's somewhat of just like a play around and make sure that you're getting the right answer. They're not like, they don't have to be completely finely tuned, but you do have to be careful when you pick, say, the amount of burn-in and how large your step size are. And you always just want to check that it's producing the distribution you want. So that I leave that as an exercise to verify that this looks like a normal distribution. And then also try to do it for a 3D normal distribution. And you can also include some, here, these are uncorrelated, these two Gaussians, but you can have some covariance if you want. And show that you can sample that space nicely. Okay, so just the last one, I thought I had to include this just because
Jayden, sorry, I have a
something
question.
would probably do all the time. But you also will want to generate random numbers from discrete distributions. And so NumPy's got functions for that. So obviously Poisson distribution is the workhorse for us. And that's just an example of generating just like numbers from a discrete distribution, like the Poisson distribution, and histogramming that. Okay, should stop there. Are there any questions about the Markov chains?
Yeah, sorry, can you hear me?
Okay. Do you want to unmute or do you want to just type it in the chat?
You can't hear us, Jay. I don't.
Can't see who asked that because my
Wait. Can you hear us, Jay?
Zoom is like showing the characters in a weird language. No, I can't hear. Oh, okay.
No.
I can.
Okay, you can hear us now?
Sorry.
Okay, can you hear me now?
Yeah.
Okay. We'll let Robert go first.
Yeah, I have a question about the when choosing the step, you're adding the normal the random when you say random.normal, you adding the Gaussian distribution, right?
Yeah.
And you said that it's important to choose the step size because you're sampling, you know, that I guess if you use a very big step size, then you can end up in a region where it never finds, you know, the way back to where you want to sample your distribution. But
yeah,
I guess in this case is just an example that you picked that part to be a random distribution. You also want to sample a 2D random distribution, right? Is there a reason why you've done that? Can you put random uniform or random?
Yeah, so you can do uniform. This is just a choice, which gives you some variance in the size of the steps. But yeah, you can definitely do uniform as well. So you could do this between 0 and, what did I say, the point? Make us up to 0.5. And then we should get a very similar answer, if not exactly the same. I mean, obviously it's not going to be exactly the same, but it should produce a very similar result. Yeah.
Because I guess this will depend on the type of distribution that you want to sample at the end of the day. Because this is not the choice that you made for the step. The distribution that you are adding to that does not affect what you want to sample, right? Because that's
like ideally you want it to not affect it.
Yeah.
But there may be ideal choices for the distribution you're sampling from.
I guess in terms of convergence, right? That's what would matter.
How quickly it converges to the
Okay, thank you.
Yeah, I ran it for 10x the step size and it took like 10 times as long, so which makes sense. I also had a question as far as like, are there any ways to get rid of like the edge conditions that you see?
So that particular one, it may have been because of the normal distribution, but like choosing a smaller step size will shrink that region. Okay. But then it will take longer to visit everywhere in the space. So yeah, it's all about with these sort of things, like just being a bit careful and making sure. like, okay, a simple thing you can do is just like cut out the middle region here. And now you've got random samples that are uniform from a smaller region. And then, so you can just like overshoot the region you want to visit and then, yeah, throw those away. Oh yeah, yeah. So we just had a suggestion here. Alexa said you could do periodic boundary conditions. So if you, in these cases, since you don't care about the Markov chain's path, you could just have periodic boundary conditions. So you overshoot one side and you come out over the other side. Yeah, that would work better.
Yeah, that makes sense. Thanks.
We can make that part of the exercise. You can implement periodic boundary conditions. Okay, so where were we? Any other questions? Was that all the questions? All right, we'll get on to the last section, which is doing some integration. So effectively, we sort of already did this. When we calculated the value of pi, we were effectively just calculating area, and then we were dividing to get pi from the areas. So we can use exactly that same method for integrating any function. So yeah, like that really dumb quick method is this: we generate random samples in a box which contains a curve, and then we look at the fraction of points that are below the curve. So as an example, I'm just doing this integral 4 minus x squared, and we're going to integrate from -2 to 2. So here we'll define the function and our min max values. This function here is useful if you haven't seen it before. So it makes it possible for the function to evaluate numpy arrays. So you just have to tell it that, you know, you take in one scalar and you give back one scalar. So now we can pass in x as an array, and we'll get back an array of x values. If that doesn't make sense, maybe it makes more sense when you look at how we do it. Okay, so we'll create a bunch of random integration points, so in x and y. So that's just this box. We fill it with x and y. Here's our function that we want to integrate. And so we count up again how many points are below, how many points are above. We're just doing that with a simple loop. And so I didn't actually run it. Counts up how many are below, and then we get as the integral 10.62, and the actual integral, if you do this analytically, you get 32/3, which is 10.66666. Then yeah, so this is pretty close after 1,000 samples, but you know, we could do better. And again, this method is not particularly efficient because we're throwing away samples. So also, yeah, this is going to be really hard if you don't a priori know what the maximum value of f of x is. So if you have to find what that is, because here I made it the most efficient it could possibly be by not throwing points above 4. But yeah, if you don't know what that is, then it's going to be even less efficient. Okay, so how can we do better than this? Well, let's revisit just the basic approximation of what an integral is as the sum of rectangles. So if you've got some rectangles of width x, delta x, and you can evaluate the function at those and sum up these rectangles, and that will give you an approximation of the integral. So if we perform n random samples of f of x, and then we can assign an average width to each sample, delta x, which is just the width of your integral divided by the number of samples you do. And as long as your points are uniformly distributed, then you can approximate the integral. This is called the Monte Carlo estimator with this sum. So we evaluated the function n times, and then we just divide by the width, multiply this by this factor here, which is the average width between the samples. So if you don't believe that works, if you can't, you can just run it and see So what this does here, now we're using this fact that we can evaluate NumPy arrays. So this is our array of random numbers. It's got 1,000 or so random numbers in there. So we can apply f to it. So that gives us back an array of the y values. And now we just sum them all together. So that's doing this part of the calculation. Then we multiply it by the width of the integral divided by the number of points. And that gives us another estimate. Okay, and it's slightly more efficient than the first method. But we could still do better. So when we look at this function, when you're integrating, especially like when we're talking about that approximation we're doing, so we're basically like adding up small boxes. The samples that are near the edges here aren't going to be contributing much to the integral. So where the y value is small, that's not contributing much to the integral. So where we'd like to concentrate most of our time is in this region here where the y value is larger. And so there's a whole bunch of methods that go under the title of importance sampling. So yeah, what we were doing above, in one dimension at least, is no better than just doing a uniform grid sampling across that function. But if we instead transform it so that we sample from the region where it's large, then we can do better than just a uniform sampling. I should note that in higher dimensions, uniform sampling becomes very inefficient, but Monte Carlo methods can do a lot better. Okay, so now if we imagine instead drawing samples from some other distribution P of X, which isn't equally weighted across here. So say we find some distribution which peaks in the middle, like a normal distribution, then we can focus our integral or focus our calculating the integral in the middle region. And yeah, so this is called importance sampling. And so effectively what you're doing is instead of calculating the integral above, we're calculating this integral, where you're weighting the values of f by some probability distribution. So before we had a uniform distribution here, so it didn't affect the integral. So now the Monte Carlo estimator that we had before looked like this. It was just sort of this standard approximation of rectangles. But now we have to weight each point by the distribution. So we just have to divide it there. And then this gives us the value of the integral. Okay. Now the trick in this one is always going to be how do you choose the shape like this importance sampling distribution P of X to be effective. So one thing you have to make sure is that it has fatter tails than your f of X function. So if you imagine choosing a random normal distribution, but it only had a width of say 0.5, so it's like sharply peaked, well, then you're never going to sample from out here. So it's not going to do a good job of reproducing the whole function. It will concentrate too much. So there's a balance here of this importance sampling of making it faster, but still, but also like making it accurate and converge faster than the normal method. It's not just a given. So it can be a bit finicky. So here I do an example where with a random normal distribution, you can play around with picking the width of the normal distribution, and you can see if it converges faster. So I've left it as an exercise to do this, and actually calculate how this converges as a function of the number of samples and compare the standard distribution we did above versus the importance sampling method. And see, you can play around with your importance sampling distribution and see what can make it converge quickest. Okay. So yeah, that's an exercise. And then the last thing we'll do is using Metropolis Hastings for integration. So if you're sort of thinking about the flow of this little workshop, I was on purpose introduced Metropolis Hastings first. So the ultimate distribution you could imagine sampling from, as in for this importance sampling, is what if P of X was just F of X? So you sample this distribution in exactly the shape of the distribution. And that seems like a bit of magic, but it does work. The only problem is that, so your standard estimator, so if we look at this, if we need to evaluate this where P of X is F of X, then this thing just becomes 1, and then this isn't telling us anything. Basically, it integrates to 1 because we've just normalized the thing we want to integrate. So to do this properly, effectively what we're saying is we need to know the result of the integral so we can normalize F of X to be able to actually compute what the integral is using this method. Now, it's not completely hopeless because, we can do this iteratively. So we can use an approximation of the integral to normalize the sampling distribution and then recursively improve the integral. And this is what's done by a very popular scheme called Vegas, if you've heard of the Vegas integrator before. Now, I'm not going to go through exactly what Vegas is doing and reproduce it, but that's the gist of it, that we use something like, we use something to give us an idea of what the shape of the distribution is, and then we use the shape of F of X to set how we importance sample the integral over F of X. Okay, so as a basic demonstration, we're going to use our Metropolis Hastings algorithm because we already used that to show we could sample from some n-dimensional function f. So this is just exactly what we had before for Metropolis Hastings, but now the step, our f of x is our integrating function. And so we can check that the distribution, the histogram distribution of our Markov chain follows this inverted quadratic, which looks right. So now we can approximate this integral by just literally using these bins and adding them up. So we do that. And then you can compare the different approximations. And what you'll find is that this one, where we've basically importance sampled from the distribution, gives you, well, okay, it didn't work there. I need to rerun it because it's using the wrong F. And we'll check it's actually working. All right, yeah, and so this isn't entirely fair because I think I did more samples in the MCMC, but yeah, I'll leave it as an exercise to make this error plot as a function of the number of samples and see which method works the best. You should find that the MCMC works the best. Yeah, so that's it. I also left another exercise just to try it for another integral, some other function. And then last of all, just to point out something that's probably more useful is that you, when you go and do these sort of things, in practice, you're not going to sit down and write your own integrator, especially every time you need to integrate something. But I like to know sort of what's going on behind the scenes, especially when you get errors or you run into issues. It's good to have some working knowledge of what these methods are doing behind the scenes. And that helps you troubleshoot and so on. But yeah, in practice, you're going to want to use something like Vegas, it's available in Python. So this is just an example showing you, you got to pip install it. It's not a standard package. Then you import it. And then I just took this example from their docs. So this is a 4-dimensional integral over something, Gaussian integral. And then they've chosen this constant so that f equals 1. But when you integrate over this whole function, it's 1. And then this is how you implement Vegas. So Vegas integrator, you've defined a function f, and then you pass it the bounds of your integral, and then you tell it integrate f, how many iterations and how many evaluations it's doing. So like I was saying, it iteratively in each step tries to approximate the distribution and then use that as the distribution of samples in the next step. So it does this iteratively. And then it gives you a step while it's going, it tells you the integral it is at each iteration. So at each iteration, it's taking 1,000 steps. And then by the time it gets to the end, it's pretty close to the true value. Yeah. Okay. Yeah, I managed to finish in time. So any other questions? No questions? Okay. Well, I encourage you to play around with the exercises, or just play around with whatever these methods, do your own problems, come up with your own problems. And then in 2 weeks, we can meet back and discuss some of these things. And I'd be interested to hear what other people have done, and we can go through some of the solutions as well. Okay. Thank you.
Awesome. Sounds good, Jay.
Cool.
See you, Jay.
See you.